Hi, today we are looking at cathode ray tubes. So we'll start out by looking at a diagram of a cathode ray tube. So this is a rough sketch of one, parts of it have been elongated to make it easier to see what's going on. But essentially we can see on the left side of the diagram we have a heater and control grid that help determine what everything in the cathode ray tube does, and we have a cathode and anodes that help with acceleration of electrons. You can see our electron beam leaves our heater control grid cathode area and ends up on the screen. We also have focusing coils and deflecting coils to help determine where on the screen it ends up. So essentially this is how older TVs and monitors work. And like how I mentioned, our electrons are being accelerated between the cathodes and anodes. And then once past the anodes, the electrons enter a magnetic field that deflects them up or down. So that'd be in our deflecting coil. Now, if this deflection is in an arc, therefore we can say that the force that caused it is centripetal. So like I mentioned, this diagram is elongated so we can point some things out. So I'll show you a picture of a cathode ray tube so you can see more or less what it should look like. So you can see that the left side of that drawing I elongated so you could see things a lot more, but essentially we have a control grid or heater on the one end, then we've got our focusing coil, a deflecting coil, and our electrons end up coming out towards the screen. So we'll look at an example. So particles are traveling horizontally at the speed of light when they enter a vertical magnetic field of 0.85 teslas. If the particles are deflected in an arc of radius of 12 centimeters, what is the charge to mass ratio of these particles? So I would start by writing out what information we have. So we know our magnetic field is 0.85 teslas. We know our radius is 0.12 meters. Our speed is 3 times 10 to the 8 meters per second because that's the speed of light. And we want to know our charge to mass ratio. So to get our charge to mass ratio, we're going to actually combine a couple different equations. Now we know that because it is deflecting in an arc, we have centripetal force. So we have force centripetal is mv squared over r. And we know the force that's causing that is our force magnetic, so QVB sine theta. Now, like I mentioned, our force magnetic is causing that force centripetal, so therefore those forces must be equal to each other. And then we're going to start rearranging this to get our charge to mass ratio, so to get Q over M on its own. Now, one thing that I'll do right off the start is we have speed on one side and speed squared on the other side, so we'll divide both sides by speed, so I'll cancel out a v on both sides. Then I will get the charge on its own by dividing both sides by b sine theta, and then divide both sides by our mass. So now we have our charge to mass ratio is equal to our speed divided by the radius times magnetic field sine of our angle. And we will substitute our values in. And we find that our charge to mass ratio is 2.9 times 10 to the negative 9 coulombs per kilogram. Next example, we have an electron traveling vertically enters a horizontal magnetic field of 0.085 teslas. If the electron is deflected in an arc of radius 6.5 millimeters, what is the kinetic energy of the electron? So we'll start by writing out what we have. We know the charge of an electron is 1.6 times 10 to the negative 19 coulombs. The mass of an electron we know is 9.11 times 10 to the negative 31 kilograms. Our magnetic field is 0.085 teslas, and our radius is need to be converted into meters. So 6.5 millimeters is 0.0065 meters, and we're looking for kinetic energy. Now once again, we have it being deflected by an arc of radius 6.5 millimeters, which means we have centripetal force. So we know we've got force centripetal is mv squared over r, and we know that the force that's causing that is a magnetic force, which is qvb sine theta. So those will equal each other. We can cancel out a v on both sides, and then we're going to rearrange this to get v on its own, so that we can then use that to get our kinetic energy. So I'll start by multiplying both sides by the radius of the arc, and then divide both sides by the mass of the electron. At this point, substitute our values in, and we end up with a speed of 9.7 times 10 to the 7 meters per second. Now we know our kinetic energy is 1/2 our mass times our speed squared. So that's 1/2 times 9.11 times 10 to the negative 31 kilograms times 9.7 times 10 to the 7 meters per second, and then we're squaring that speed, giving us a kinetic energy of 4.3 times 10 to the negative 15 joules. Now we won't just deal with magnetic fields in some ways. In some cases, we'll also have electric fields. So by adding an electric force in the opposite direction, we can reduce the amount of deflection or prevent it from occurring. So if our electric force is made to be equal to but in the opposite direction as our magnetic force, we will have no deflection. So we'll look at an example that integrates this. So what is the speed of an electron that passes through an electric field of 7.5 times 10 to the 3 newtons per coulomb and a magnetic field of 8.5 times 10 to the negative 3 Teslas undeflected? So for this, we're going to assume, because it's undeflected, our force magnetic and our force electrostatic are equal but in opposite directions. And we'll start by writing out what information we have. So we know our charge is 1.6 times 10 to the negative 19 coulombs. Our mass is 9.11 times 10 to the negative 31 kilograms. Our electric field is 7,500 newtons per coulomb. And our magnetic field is 8.5 times 10 to the negative 3 Teslas. We know our force magnetic is equal to our charge times our speed times our magnetic field, while we have our electric field is equal to our force electrostatic divided by our charge, which if we rearrange that, our force electrostatic is equal to our field times our charge. Now our forces must be equal to each other for it to be undeflected, so we can say our EQ equals QVB. Now we want to solve for the speed, so we're going to gradually start rearranging for V. However, what we'll notice first is we have the charge on both sides of the equation, so that's going to cancel out. And then divide both sides by our magnetic field, substitute our values in, and we get 8.8 times 10 to the 5 meters per second as our speed.